This is the note that we saw at the end of class today. We did a demonstration on skating, what happens when you're on a level surface and you're pushed or not pushed, or if you're already gliding and you receive a push or don't receive a push. So we showed you all those demonstrations by skating around the room. Inertia was the main idea that we pulled out of that. That inertia is your body's tendency to do what you are already doing. So if your body's resting, you want to stay resting, and if your body's in motion, you want to remain in motion. The only thing that can change those two states is if there's this outside net force acting on you. That's more in a later chapter, but right now, just think of it, there's got to be something to accelerate you, either bring you out of rest or bring you back to rest or change your direction. What we're talking about here is projectile motion. Projectile motion is nothing more than this. Launching an object through the air, watching it accelerate as it moves from one location to the next, giving that object an initial velocity and watching it travel along this parabolic path. Oh, come on, let's go. Yes, yes. Perfect. So when you get really good at projectile motion, you become really good at Angry Birds. For projectile motion, it's an object that is projected by any means, and the only thing that acts on it is gravity. If gravity is the only thing accelerating this object, we say it has become a projectile. There are two pieces to any projectile. It's got two components. It's got a horizontal component, which you can think of something just rolling across the surface of the floor, sort of like I did in class today when I rolled across the floor and I was in motion and I kept staying in motion. So the horizontal component is always constant velocity, and it's got a vertical component. The vertical component is similar to things that are in free fall, just like when we drop things or when we threw things up in the air. Things will accelerate in the vertical direction, and it will stay constant in the horizontal direction. And the nice thing about projectile motion is that each component, X and Y, are completely independent of each other, meaning you can solve a whole problem dealing with all of your X pieces and then solve the problem also using just your Y pieces. So I would recommend making two columns, and I'll show you how to do that, so that you can keep track of what variables you know and which ones you're still looking for. Like we showed in Angry Birds, when you launch something at an angle, it has this initial horizontal piece. That's the initial velocity in the X. It also has this initial velocity in the Y. So as soon as you're given an initial velocity and an angle for projectile motion, the first thing I would do is break them into their X and Y pieces. For this segment, I'll ask a question and see which component, the horizontal or the vertical, controls different parts of a projectile. The very first thing would be the range. How far horizontally does the projectile go? Or the component that controls the horizontal range is X. So we call the horizontal displacement a range, how far it travels. Obviously, the vertical component would be controlled by the Y. That's the height. If we are just sending this object straight off of a cliff, which component here would have an initial velocity of 0? Well, if the object's rolling straight to the right, that means it has an X component already, which means it hasn't fallen off the table yet, so there is no vertical component. So the initial here is 0. So Y takes control of that. The next one is which one controls free fall acceleration. Well, since free fall acceleration is a vertical piece, we know that the acceleration due to gravity will be g, up and down. The last one, which component here is going to control the time of flight? Is it how far you go out? Is the horizontal piece going to control time of flight, or is it the vertical piece that controls the flight? And the way that I can try to get you to remember this is if you were running straight off a cliff or straight off a diving board and there was no gravity, would you ever hit the ground? And the answer is no. You would just continue off in a straight line at a nice steady speed. Time must be controlled by the vertical component because gravity accelerates you down towards the ground, will cause you to reach the ground, and controls the time that you're in flight. So if a projectile is shot at an angle, though, we've got a couple other things to consider. I said that the initial velocity in the y direction was 0, but that would be if you were just firing something horizontally. Here, in this projectile motion, you can see that there is an initial x and y piece. As the projectile flies into the air, the initial x piece remains constant. The y piece is getting smaller. When you reach the peak, we know that objects stop, but that's only in the vertical direction. So you can see the Vy at the top is 0. The Vx is still the same as it was when it left the ground. And on the way back down for the arc, the initial and the x is still constant, and the y is now growing. And since projectiles travel in nice parabolic paths, we can do quadratic equations like we did before and find the roots to figure out when the object will be at its initial launch point and when it will be back down to the ground. So if you break your problem into the x and y components, you'll find 2 roots for your problem. And sometimes when you launch projectiles, they don't land perfectly back on the ground. They could be caught up in a tree, or they could land way down here like it's showing you negative 100 meters below its start point. What you need to do is, again, write down all your variables, know what your initial conditions are, and then solve for your final condition. Some numeric examples you can follow through. Here we have an object rolling off a hill with an initial speed of 5 meters per second, and you can see that once it leaves the cliff, we know that projectiles will follow this curved path. They want to keep their horizontal motion constant. They start to accelerate as they fall to the ground, so those 2 motions act independently of each other as the ball reaches the floor. The way I like to set these up is put an x and y column, and in each of the columns, what you're going to be looking for is a displacement, so a change in x or a change in y. You're going to be looking for an initial speed, a final speed, an acceleration, and a time. Those are the 5 variables you're going to look for on both sides. So as we look at this initial problem we've got here, initial speed is 5 meters per second in the horizontal direction. And since the ball hasn't fallen off the cliff yet, there is no initial speed in the y direction. It has not fallen down yet. One thing we do know about acceleration is that the horizontal motion is constant, so there is no acceleration, which means the final speed must be the same as the initial speed. Over here in the y direction, we don't know how fast it's moving right before it hits the ground, but we do know it's accelerating towards the ground at negative g. Right off the bat, out of the 10 variables I'm looking for, I already know 5 of them. And usually the problem will tell you how tall this cliff is, so if we said this cliff was 20 meters tall, you now know a displacement of negative 20 meters downwards. As this thing falls, looking on either side, you could solve for displacement in the x or time in the x or y. The nice thing is that the time on either side is going to be the same. The time for the marble to go out is the same time for the marble to fall downwards. If you solve on either side, say you get some time in the y direction, you can use that time in the x direction to solve for the displacements or anything else you might need. I'll solve the y out and try and solve the x out on your own. Using the information that I know, in the y direction I don't know the final speed or the time. Final speed's interesting, but more important, the time. How long is this thing in the air? Using your kinematics, I knew that the initial speed was 0, so goodbye this term. I want to rearrange the formula symbolically. 2 times the displacement over acceleration gives you time squared. Square root that gives you the time for fall. Plugging in the values you know, 2 times 20 is 40. 40 over, let's say, 10, just to make it easy. That's 4. Square root of 4 gives you 2 seconds of free fall. It takes 2 seconds for the object to fall. It's also going to take 2 seconds for the object to fall out. So what I'll ask you to do for homework is tell me this. How far out here in the horizontal direction does the marble travel before it reaches the ground? Basically, what is the horizontal displacement? In the second example I have here, we have ball being launched at an angle, and instantly what you'd want to do if I gave you that initial speed is you'd want to get its x and y pieces. In this case, it looks like your x component is going to be VO cosine, and it looks like your y component is opposite, so it's going to be VO sine. Once you do that, what you've essentially done is erased this angled velocity. and now you have an upward velocity and a left and right velocity. So what you want to do is, again, organize yourself. What you want to have is an initial, a final, an acceleration, a displacement, and a time. Things that are known off of that angled projectile problem. We know that the acceleration here is negative g. The horizontal direction is 0 because you're moving at constant velocity, just obeying your inertia. The initial velocities, we just broke them up. We know that this is VO cosine of theta. And on the way up, the vertical direction is VO sine of theta. Final speed, let's leave that alone for the y direction, but final speed in the x direction is also VO cosine of theta. The horizontal component never changes. Displacement-wise, if they ask you at the highest point, you could figure out how far the object's traveled in the x direction. The y direction, we would know that at its highest point, the final velocity is 0 at the top. If they ask for all the way back to the ground, you would know that the final velocity would be the same as the initial, just in the opposite direction. The displacement would end up being 0 if we took it to the ground. But looking at what you have here, you should have enough information to solve for displacements or times. And remember, if you solve for time, time in the y is the same as time on the x. So you can use it on both sides. As soon as you get time, time is a huge thing to find for projectile motion. And the last thing I want to show you here is a projectile problem, just like we showed you, but giving you some heights, giving you some speeds, and watching the ball move through its path. As I start the motion, watch that horizontal piece constant the entire time. You can see the vertical piece. If I reset it and watch it again, the vertical piece starts from 0 and gains velocity on the way down. If I wanted to ask where the acceleration was, well, horizontally that x piece never changed its velocity. So the acceleration should be 0. And if the y piece is gaining velocity, there should be acceleration downwards. So if I show just the acceleration on the ball as time goes on, it's constantly accelerating down towards the ground. We can put this back on the ground and launch this object at a particular angle. And when you do that, you can see that you get an x and y component. The true velocity is right here. A radar gun would read whatever the hypotenuse of these two velocities are. But if I start it, you can watch that as you reach the top, that y velocity is 0. The horizontal speed has not changed. And on the way back down, the y velocity grows. We can reset this again and watch just the acceleration vector. We'll actually put all three on. And you can see vertical velocity decreased, then increased, and horizontal velocity stays constant the entire trip. And the last little bit here for angle projectiles is something that happens with the angles that you launch at. Or when you launch projectiles at different angles, depending on what angle you have, as long as the angles are complementary, meaning like 70-20, 30-60, 53.1, 36.9. As long as those two add up to 90 degrees, they'll land in the exact same range. The timing will be different based on how high one of the objects goes